In Module 3, we now turn to the question of simulating log-normal stock prices. And the notion of simulating really is closely related to the notion of creating a sample. And that is that if I wanted to simulate stock prices at time 2 years, given a certain model, I have a log-normal distribution, I would calculate or I would sample from that time 2 years log-normal distribution. The notion of simulation, however, often applies to the notion of sequential sampling, whereby instead of only being interested in the stock price at 2 years, I might be interested in the monthly path of stock prices that occurred from time 0 to time 2 years. In other words, how did this time 2-year price evolve by determining the stock prices at time 1 month, 2 months, 3 months, and so forth. So a simulation can be one whereby one creates a sampling of a price at a given time point, or it could be a simulation of a path of prices is the usual terminology, but it's a sequential sample where one thinks of all possible price paths that can occur from our lattice, and we're sampling from that collection of price paths. And we can also think of that as we're simulating the evolution of price from S0 to its ultimate price at S at time 2. So there are several ways of doing this. The whole question is generating randomness. And one of the key things that is necessary to generate random samples is to, in fact, generate a simple uniform distribution. It turns out that if I can generate randomly a uniform distribution between 0 and 1, that can be applied in quite a variety of contexts that are useful in finance. And I'll discuss some of those applications in a moment. Excel has a built-in function called rand, which generates random numbers between 0 and 1. So, for example, if you, in a cell of Excel, type equal rand open paren, close paren, and copy it down through 100 cells, you will observe 100 random values of a uniformly distributed random variable distributed between 0 and 1. And if you hit F9, that collection of 100 sample points will keep recalculating, and you'll keep getting additional samples of 100 uniformly distributed random variables. So it's easy to generate in Excel and many other mathematical softwares, easy to generate this uniform variable. Those can be used directly in finance, as we'll see. You can also generate random numbers that are normally distributed. And of course, what we really need is Z, because we know that if we can randomly generate standard normals by multiplication and addition, namely specifically, if we do sigma Z plus mu, then I can generate normal random variables with the mean of mu and the variance of sigma squared. So the key is, how do I generate a standard normal Z? And once again, there's a couple of ways of doing it. One approach to doing it is this approximate method using basically the central limit theorem. And the central limit theorem, you recall, says that if I take an average of random variables and subtract the mean and divide by the standard deviation of that average, it converges to the normal as n gets big, as the number I sample get big. Turns out that convergence is pretty quick when I start off with a uniform distribution, and here this is using it, that if I generate 12 uniform variables, say using the rand function, and I add them up and subtract 6, then and the standard deviation of that sample is 1, then I get an approximate normal. It's not a terrific approximation, but it's a crude and rough and ready approximation. And I say at the bottom of this next slide that, in fact, you can do this in Excel. And let me set this up a little bit. Another application of generating random samples from various probability density functions is a general procedure which, again, uses uniformly distributed random numbers. This is another application of randomly generated uniform variables, and that they can be used to generate a random sample from any distribution if you know the distribution function. And the basic idea is we generate a random variable x, and then we use the inverse distribution function. I'll show you this graph in just a moment. The inverse distribution function. So the randomly generated variable is the x, and then z is deterministic. It comes from the inverse distribution function that you want to work with. And I'll show you that in just a moment. So you generate random x's. You use the inverse distribution function to get the randomly generated z's. An application in Excel is that in Excel, the built-in function norm s inv, that's the standard normal inverse, is in fact the inverse of the normal distribution, the standard normal distribution function. And by combining it with the rand function, you can generate randomly distributed standard normal variables. You notice how I'm using the procedure. Rand generates a random uniform variable. Norm s inverse, is the inverse cumulative distribution function. So it's basically n inverse of x. Excel also has other inverse distribution functions, because this is an important procedure, and it can be used with any distribution function where you can calculate the inverse of the distribution. So Excel gives you a variety of distribution functions where you can calculate the inverse. But let me show you graphically what is going on.